started then? Recording? Excellent. Boom! How is everybody today? How did the test go? Easy? Yeah.
It's so hard. Your class today make it actually easier.
Yeah, we'll see about that. So, it wasn't as big a bloodbath as I was expecting, which is good. Class average, I believe, was around a 75%, which actually I think is fantastic. I may have said this at some point, but just to calibrate your expectations to a university environment with respect to grades, I don't know what they're doing in high school these days or elementary school. The general impression is that they just give literally everybody 100% on everything because to mark people down on anything would be discriminatory. So in general, what a B is supposed to mean is that you are meeting the expectations of your professor or instructor for the course that you're taking. So if you got something in the B range, you shouldn't like, you know, throw your hands up and say, well, I guess I'm going to go become a plumber then. In general, a B is a good grade. In general, an A is a better grade. Of course, you know, there are some people who are in medical school or trying to get into medical school who require exactly straight A pluses. They usually have dropped the course by now. So, yeah, if you get a C, it's not the end of the world, but, you know, perhaps an indication that you should pull up your socks and study a bit harder. If you get a D, you may want to study a lot harder. If you failed the test, there's probably some kind of structural problem that you should address, either in the manner in which you're approaching the problems or the way that you're studying, right? So people kind of have, I find particularly, you know, this is getting worse as history progresses towards the big crunch. People are generally becoming more anxiety-prone and anxious. One of the features of anxiety is that you have a tendency to catastrophize, or that is to say, when you receive a negative feedback or a negative result, your tendency is to not examine that negative result at the correct level of abstraction with respect to your entire life. A bad grade on a test is just a bad grade on a test. It does not mean that you are fundamentally unsuited to the degree program you are pursuing. It does not mean, again, that you should quit university and become a plumber, although it would probably be better for society if more people quit university and became plumbers, because there's not enough plumbers or tradespeople in general in our society. You know, that's a whole different discussion. But in general, if you flunked the test, you know, take it as a slap in the face, because it is. Take it as a wake-up call, because it is, right? And do better on the next one, you know? I was talking to a few students in my office hours yesterday on the subject of not just the test, but kind of like the mechatronics class also had an assignment that they got feedback for over the break, and like you know, there were a few instances of butthurt in that class as well, because they're being held to the same standard you are, basically, where their code actually has to work for once. I'm not sure what they're doing in first year, because like a lot of them come out of first year with the impression that they should receive grades for code that doesn't even work. But you know, anyway, that being held to the side for the moment. One person who came by my office hours sort of asked me, I think, a pertinent question. This particular student had the problem that basically what brought their mark down on the test was kind of cascade of small errors which occurred because, you know, it's a test and you don't have much time and it's a high-pressure environment, right? And the student put to me a very general question, which is, how do I avoid all of these small errors that were suppressing my grade? And I think that might be of general interest to have answered. So it's kind of a tricky one. The metaphor that I proposed to this particular student was, imagine that this is a carpentry class, right? And you're all apprentice carpenters, and I'm trying to teach you how to build a cabinet, or build a, cabinet will do. So we had a test, and a fair number of you managed to build a nice looking cabinet, right? But for a fair number of people as well, the hinges were on crooked, and there were nails sticking out at odd angles, and things weren't nailed together particularly well in some cases. And the question is, well, how do I build a better cabinet? And the answer is, of course, one nail at a time, right? What it requires, I kind of think of programming more as a craft than any sort of other intellectual, rather than it being sort of pure intellectual exercises. You're trying to build a thing. The thing that you're trying to build is abstract and composed of data. That doesn't change the fact that, workmanship is a sort of important quality of code, right? So what it requires is sustained concentration and sustained attention to detail. And you have to be able to follow all of the micro procedures exactly and compose them into a larger, thing. In this case, software. So, one of the pieces of advice I gave, and I know I'm going to sound like everybody's dad when I say this, but one of the pieces of advice I gave is look after your basic biological mechanisms. Make sure you're getting enough sleep. Make sure that you're eating food that isn't junk food all the time. That kind of stuff. It's really surprising how much just looking after those things will improve your general ability to concentrate on problems. So, that's the advice I would give. You're welcome to take it or leave it. It's kind of one of the cruel facts about the university that, if the advice goes unheeded, the only person you have to blame for your failure is yourself, basically. So it goes. Any questions in general? Or specific? Yes?
How should I easily approach to a conclusion?
How should you easily approach which?
How to program a conclusion? Because nowadays I'm trying to do those functions such as even Python, but also Excel.
Mm-hmm.
I still don't know how I should approach to program my conclusion easily. It's so confusing.
Yes. So the question is, how does one easily approach recursion and the programming of recursive algorithms? The answer is that there is no easy approach. Recursion is a more difficult topic than, programming recursively is more difficult, period, than programming in an imperative sense. In order to program recursively, you really just have to, absorb a more mathematical way of thinking about programs, right? You have to think in terms of the data structures, right? You have to think in terms of refinements of data structures. You have to think in terms of iterative refinements of data, right? you have to think in terms of sub-problems, right? So one of the key sort of abstractions that's required to think recursively is to be able to take a problem and visualize it in terms of sub-problems, right? So, you know, and this kind of slides nicely into our lecture material today, so thank you for the question. So with respect to the factorial, you know, our much beloved factorial example, you have to be able to think of the factorial as a thing that contains sub-instances of the same thing, right? You have to be able to think in terms of quasi-circular definitions. But we've kind of done factorial to death. This base case, iterative case formulation is frequently used, excuse me, but it's not the only formulation that recursions can have, right? So it's common, and it's you know, an excellent starting point, but recursive algorithms in general get more general than this, let's say. So yeah, you have to sort of bend your mind to think in an inductive fashion, right? You have to be able to, number one, think about how a problem could be solved in terms of sub-problems of itself, right? And you also have to think about how you might, like where that stops. What's the stopping point of that decomposition, right? So the manner in which a problem is decomposed into instances of itself is the iterative case, or the inductive case. The base case is that which can no longer be divided into sub-instances of itself. Am I kind of making sense? Yeah. I almost want to bring like examples in from second year, but I think it's probably best to just keep going with the slides, because we're going to talk about the Fibonacci sequence, which is sort of a classic inductively defined sequence of numbers. So, so the point of this slide, basically, is to demonstrate that as you step into recursive calls to the same function, they are not finished before, like we still, at all points, we have actively open all factorial, all calls to factorial that have preceded the current one, right? So when we call factorial with n equals 5, that asks us to open factorial with n equaling 4, equaling 3, 2, 1, and 0. We have not concluded any of these calls to factorial prior to the conclusion of the n equals 0 case, right? So we return from the base case, right? The result of n equals 0 is calculated, passed to n equals 1. n equals 1 is concluded. That's passed to n equals 2, etc. Right? So you're kind of stepping down into layers. It's kind of like an algorithms are like onions type problem. You solve, like, if you consider the structure of an onion, right? You've got a number of concentric shells of onion flesh. Each one is smaller than the one that went before it, but they're all nested inside of each other. That's like, you know, metaphors are not a good way of describing formal mathematics, but, you know, it might get you part of the way there. So, every time we recurse, the interpreter creates a new scope for the variables of the function. So, if we have variables declared, or if we don't, we will still have the arguments to the function, which in Python count as variables in the regular sense. So, every instance of factorial which is called maintains its own copy of n, holding its own value, right? That's why this works. That's why when factorial is called with n equaling 2, it doesn't overwrite n when we had previously written 5 to it, right? It's a separate instance of the variable. I think this is a little bit more clear in Python Tutor. You guys remember the example I did in Python Tutor? Okay, good. So you might be saying to yourself, this seems a little advanced for a first semester class. Aside from the fact that you guys are hypothetically learning Haskell and 1JC3, and that Haskell exclusively uses recursion as its mechanism for calculation, period. How is recursion useful? Well, recursion is a natural technique for solving problems with an inductive structure. It turns out that there's a huge class of algorithms which have this structure. Not only do they exist, they are among the best algorithms in existence. So there's more, again, recursion is a more general technique than this, but one thing recursion is used for is the so-called divide and conquer algorithm, which we're going to see an example of when we talk about searching. So the idea of a divide and conquer algorithm is that you take some field of data, perhaps, you make a decision about that data, and you are left with sub-instances of the same problem. Normally, you're sort of shooting for dividing it into two equally sized sub-algorithms, right? You then recombine these sub-algorithms in such, or you recombine the results of these recursive calls in such a manner as to preserve the property you're trying to establish. And I know that's like kind of highfalutin language, but an excellent example of this is an algorithm called merge sort. Now, we're going to talk a little bit about, you'll get your searching algorithms definitely in second year, a good and thorough treatment of them. But essentially, the sorting problem is you have an array, or a list, or a tuple, and you want to put the elements in some kind of numerical order, either ascending or descending, it doesn't matter, right? The merge sort algorithm, you take this array, you split it in half, you call merge sort recursively on the two halves, right? That splits the algorithm up down to the level of the individual elements of the array, right? And then you have the recombination algorithm, where you trace through two arrays, and whichever, starting at the beginning, whichever one has the lowest element, you put that in the result array, and then you move up. And you keep doing that until you run out of elements to add to the resultant array. And that's the merge in merge sort, right? Once you've done that, you have a resulting array that has all of the elements of both of the arrays that went in and is sorted, right? You have that combination follow its way back up the tree of recursions that were called, and by the end, everything is sorted. This technique is more efficient than pretty much all standard techniques, standard non-recursive sorting techniques. Merge sort can accomplish sorting in worst case n log n time, which you don't have to worry about understanding what I'm saying at the moment, but you will eventually. Whereas sort of your basic sorting algorithms can only manage it in n squared time, and n multiplied by log base 2n is much less than n squared over time. So it's recursive algorithms. Once you get into algorithms as a subject, a solid understanding of recursion will need to have occurred by then, if that makes sense. Hopefully you'll be able to pick up a bit more of it when you study more formal mathematical techniques and inductive definitions, inductive proofs, that sort of thing. Any questions? Okay, so depending on the structure of the problem, recursion can be inefficient. Recursion is not a panacea which solves every problem. Well, technically speaking, recursion can solve every problem. The question is whether or not it does so efficiently. Like, you know, any program can be written in any Turing-complete language. Languages based on recursion are also Turing-complete. Therefore, languages which exclusively use recursion can implement any program written in any imperative language, right? They can perform the calculation, but the question is, how efficiently can they do so, right? Everything I'm talking about is a sequence of tools to be applied to specific situations, right? There's no general best technique. Make sense? Good. So let's talk about the Fibonacci sequence. How many people have not heard of the Fibonacci sequence? Good. So the Fibonacci sequence, inductively defined, if we were to define it using the same structure as we defined factorial with, if n is equal to 0 or 1, the Fibonacci of n is 1. Otherwise, the Fibonacci number of n is equal to the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. So, this is still a recursive definition, as we have invoked the definition of the Fibonacci sequence inside of our definition for the Fibonacci sequence twice. Make sense? So, let's code this bad boy up, shall we? Cue coding example. Yes?
Just have a different question. Like in the Python, is the tail recursion side, is it
Oh yeah, you can certainly do tail recursion in Python. Yeah, absolutely. You just, you know, you have to be a little careful with tail recursion though, because remember, right, Python uses pass by assignment inside of functions. So if the thing that you're attempting to tail recurse on is a mutable data structure, such as a list, if you, like, you know, pop the head off of the list and then pass that back, right? If you expect the list to be in any way intact, like, that breaks the that business where each, like, in that case, all recursive calls will not have their own unique version of the list because everything's passed by assignment. Assignment on lists means that you're aliasing, right? So you have to be careful with tail recursion in Python because you might run into aliasing and you might be modifying the data structure outside of where you think you're modifying the data structure. So use tuples if you're going to use tail recursion. Done. Easy. So, Fibonacci. call it Fibbo. Because why not? That's funny, right? That's memes. So, similarly to our factorial example, we have a base case, iterative case implementation. So, if n is equal to 0 or n is equal to 1, return 1, else return fib n minus 1 plus, fibbo, pardon me, n minus 2. So, good. And we'll just print Fibbo on 10. Python 3, topic 5.9. I'm going to save that first. There we go. Boom! The 10th Fibonacci number is 89. Is that, like, should I kill the lights a little more? Is that too dark? Yeah, yeah, okay. How's that? Is that better, or would you like it a bit more? Is that good? Good? Okay. So, good. Fine. I've basically got the next, rest of this section memorized in my head. So I'm just going to do it in code, and then, we'll go through the slides. I'm informing you that I'm doing this ahead of time this time, rather than just doing it like I usually do. So, here's the so Fibonacci, right? Good. So let's say, just for the sake of interest, we wanted to calculate a somewhat higher Fibonacci number, right? So 20, fine. 25, fine. 30. You see how it had to wait a little bit there? I'll run that again. So in Linux, there's a neat little command that you can use to time how long a program takes to run. It's just called time. So if you time Python 3 topic 5.py, there we go. You can see that it takes about a quarter second. So let's try 31. No, not D. What are we doing with D's in there? There we go. Uh-oh. 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 So, we can see that while this method of calculating does work, we can't, in a reasonable amount of time, calculate anything past the number 40. Right? This is taking too long. Most people at this point will think that the program has entered an infinite loop. In fact, it has not. It's just still crunching that number. All right? So this is this relates to another computer science topic, which is the undecidability of the halting problem. Right? So there's no program which can be written which will determine if another program terminates or not. This is known as the halting problem, right? Yeah, there we go. Takes the better part of a minute, right? So the question we might have is why, right? So for I in range from 0 to, let's say, 41. Count by 5s. Num-log, there we go. Remember, the second one is like goes to 1 minus that number, right? So if I wanted 40 included, I have to do it that way. So fib of string convert I equals, there we go. So let's do one more modification. This is one of the only instances where I condone the use of global variables, but let's see how many times that function is actually being called, shall we? Because it's a damn simple function to be taking so long, right? So we must be calling it a lot more times than we think we are, right? So let's say we have a global variable, iterations. Actually, I could probably just put it in here. Global iterations, iterations plus equals 1. Print fib was called, string convert iterations times. Right? Question? Speak up, please.
We want to change the 42 and have it.
Oh, yeah, pardon me, yes, thank you. Good call. Right, so let's execute this thing. Actually, you know what? I think I'm gonna do it a little differently. We'll only go to 30 and we'll go by ones. Or 30, there we go. Just think that'll be a better demonstration. So, you will notice, for base cases, obviously we only need to call a thing once. But you'll notice, as we go down here, the number of times that Fibonacci is called is going up substantially, shall we say, with each new additional digit that we add, or each, not digit, every time the number goes up by 1, you'll see that the number of calls we have to make to the Fibonacci function is roughly doubling. Not quite doubling, it's like being multiplied by like 1.7 or something on that order, but it's roughly doubling each time we call for incrementing fib by 1. So, there is a structural reason for this. In the program itself, can anybody spot the structural reason for this behavior? Yes?
The return statement calls two different instances of Fibonacci, so it'll extend to many different stacks of that same function.
Precisely. So, if we examine the return line here, you'll notice that we are making 2 calls to Fibonacci for every 1 call that we receive, roughly speaking. This does not, this discounts a sort of a degree of raggedness at the end of the tree, so to speak, which results from the, it's not perfect doubling, but it's approximately doubling, because every time we call fib, we spawn 2 more instances of fib if it's not a base case, right? In terms of computational complexity, that makes this big O 2 to the power of n, where n is the number itself which we are calculating. So we're in absolutely terrible territory, because normally when we talk about computational complexity, we're talking about the number of inputs, that is, like the size of the array. Here, we're talking about the magnitude of the number itself, causing computational explosion. So this is an extremely bad algorithm. Make sense? So, let me just, I think, there we go. This is the problem, right? If we were to calculate fib4, we would require calls to fib3 and fib2. Fib3 requires 2 and 1, but fib2 requires 1 and 0. You see? You see what we're talking about? If we wanted to calculate fib5, we would put fib5 like up here, and then we would also have to calculate fib3 and be an exact duplicate of this branch of the tree. Right? That's what we've asked the computer to do. The computer does not perform these types of optimizations on its own. That's for you, the intelligent programmer, to design. So, does anybody have any idea how we might go about improving this situation? Let me see if somebody else knows. Yes.
Caching the values?
Caching intermediate results. Yes. Caching! So, caching is an extremely important technique. Like, it is impossible to understate how important caching is to the development of efficient computer systems. What caching is, roughly, you spend a little bit of memory, you gain a lot of runtime, right? Or you lose a lot of time you had to spend. You know what I mean by gaining runtime. I don't mean it spends anyway. Anyway, so you may notice that fib2 is recalculated when it's called for. If, rather than recalculating these values when we need them, we store the results of these calculations somewhere inside of the program and call them out when we need them, we can avoid this, exponential expansion of the tree when we increase n. So let's examine how we might go about doing that. So there are a couple of ways of doing this, of course. One requires, like the typical Python one would be to define a dictionary to do this, but you can do it slightly more efficiently if you make an array. Array access is faster than dictionary access, and in the end, when the data structure that we're storing these intermediate results in is fully populated, we will, in theory, have one Fibonacci number calculated for all of the natural numbers up to the number we're trying to calculate, which means, in a more formal mathematical sense, what an array is a mapping between the natural numbers and some other numbers. So this would be an instance where, you could use an array or a list quite easily, but for now, let's just do a dictionary because they're easier to sort of construct from the top down, and they make a little bit of sense. All right? Make sense? Either would work. So, what the slides call this is memoization. All right? As far as I have been able to discern, and I have a PhD, memoizing and caching are pretty much exactly the same thing. So if you see the word memoization, it just means caching. All right? So let's say we have a memo. By default, the memo shall be empty. This means that we don't have to create the memo outside of the function and pass it in. An empty memo will be provided by default if no memo has been provided. This sort of normalizes the external interface so that it doesn't change, we won't have to change the manner in which Fibbo has been called later on in the program, which is like, whenever you're making modifications to programs, you want to change the interface as little as possible. That's like a good design technique, right? So, fine. So, what we want to avoid is these two direct calls to the Fibonacci function, right? So, what we want to do, first, check to see if the number is in the dictionary. If it's not in the dictionary, we add it to the dictionary. And if it is in the dictionary, we just use the dictionary value, right? So, let's do fib n minus 2 first. If Fibbo at n minus 2 is in the memo, then we set some variable to memo at n minus 2. Otherwise, we put it into the dictionary. So memo at n minus 2 is equal to Fibbo, or sorry, I made a mistake here. We want to check to see if n minus 2 is in the memo, not the result. Because remember, the in operation on dictionary searches the keys, not the values. I apologize. So, also that would put a call to fib into the conditional of the if statement, which would be the height of bad manners. So, then, once we get down here, we can just replace that with F2. And now we use the programmer's secret weapon, copy-paste. Not from other people's assignments. That's plagiarism. Oh, I've got a syntax error there. There we go. Now, and I know this isn't sufficient, that we're getting there, don't worry guys. We still could squeeze some efficiency out of this, but,
F1 is not in scope.
Oh. Oh yeah, right, yeah. There we go. So, you'll notice that this long sequence that we executed in 0.125 seconds before now executes in 0.025 seconds. And when you're used to the time function, basically there's nothing that won't register at least that much. So we have improved things. So let's see. Can we calculate up to 50? Easily, in the same amount of time. How about 500? The number gets quite long, but still executes in very little time. How about 1,000? Again, the numbers are getting quite long, but the runtime remains stable. Question? Caching is a more general term. It refers to the use of memory to store intermediate results. Yeah. In this, no, we're using a dictionary. You could use a list. A list would also work, but in this case, we're using a dictionary. So, this is a more efficient algorithm. The amount of time that it would take this, it would take the uncached, unmemoized version of this algorithm to calculate the 1000th Fibonacci number would be likely far in excess of the age of the universe so far. No, in a very literal sense. It's like, what's 2 to the power of 1000? Right? Very, very large. And consider that the universe is only, what, like 14 billion years old? Something like that? So, at least according to scientists. So yeah. So just as an intellectual exercise now, we can squeeze a little bit more efficiency out of this by simplifying the code on the screen here. I wrote it this way because this is this is the most direct, interpretation of the manner in which I described the algorithm. But there are some simplification techniques we can now employ to reduce the size of the code here. So, first of all, can anybody think of one? Yeah. I'm sorry, can you speak up?
So, instead of putting a dictionary and passing it into the next one, we can instead include a twofold with the first number and the next one.
Yeah, so you could improve, well, you could do things eagerly, right? You could populate the dictionary first and then calculate the Fibonacci number. I'm not sure if that's what you're talking about. By the way, I forgot to include the actual passing of the memo, which is kind of funny. It's kind of funny that it works anyways, but does anybody have any idea why that works anyways? I forgot to pass the memo in, but it still worked. Yes? Say again? Well, me setting it as an empty dictionary at the beginning of the function sets it as a dictionary, otherwise Python doesn't know what type it is, so that was good, right? But that's not, that's not why I could, cache these results without actually physically passing the dictionary through. Yes?
Memo is a mutable data structure that's inherited by all the results.
Yes. So memo is a dictionary and therefore a mutable data structure. Because it's a mutable data structure, any modification to it is seen by all things that have a reference to it, which include all recursive calls. So it automatically picks up all of the modifications which are made to it as we go through the algorithm. However, it is certainly better programming to pass it explicitly. Make sense? So, very simple simplification. If you have a single statement which occurs at the end of both branches of an if statement, it will be executed regardless as to whether that condition comes out false or true. Therefore, it may be removed from the if statement and placed afterwards, thus briefly simplifying things. Now, we have an if statement with an empty if branch and an else branch that has stuff in it. We simply remove the else and include a not. Right? This making sense? Hopefully. Furthermore, the only purpose of F1 and F2 here is to store the results of calls to simply read elements out of a dictionary. We can remove these entirely and replace them for, for the uses of those variables inside of the return statement itself. Thus, we can shorten the code quite a bit. Now, is that nicer to read? Is it nicer to look at? Would you prefer that your mom put that on the fridge or the other one? Right? No. And just to demonstrate that this still works, it still works. Cool. All right, thank you very much, everybody, for your time and attention. See you whenever I see you.